Next, we have to continue online class, third year max, and then subject is real analysis 1 theorem. If n varies from 1 to infinity is a sequence of positive numbers such that subdivision a1 is greater than or equal to a2 is greater than or equal to etc. greater than or equal to an is greater than or equal to an plus 1 greater than or equal to etc. Subdivision b, limit n tends to infinity, an equal to 0. Proof. Consider the partial sums with odd index s1, s3, etc. We have s3 equal to s1 minus a2 plus a3. Since by subdivision a3 is less than or equal to a2, which implies s3 is less than or equal to s1. For any n belongs to cap psi, we have s2n plus 1 equal to s2n minus 1 minus a2n plus 1 less than or equal to s2n minus 1. Thus s1 is greater than or equal to s3 is greater than or equal to etc. greater than or equal to s2n minus 1 greater than or equal to s2n plus 1 greater than or equal to etc. Therefore s2n minus 1 n varies from 1 to infinity is non-increasing. Hence s2n minus 1 n equal to 1 to infinity is convergent. Similarly, the sequence s1, s2, s4, etc. s2n is convergent. For s2n plus 2 equal to s2n plus a2n plus 1 minus a2n plus 2 is greater than or equal to s2n, and so s2n n varies from 1 to infinity is non-decreasing but also s2n equal to a1 minus a2 minus a3 etc. a2n minus 2 minus a2n minus 1 minus a2n. Thus s2n is less than or equal to a1, so that s2n n varies from 1 to infinity is bounded above. Let m equal to limit n tends to infinity s2n minus 1, and let l equal to limit n tends to infinity s2n. Since a2n equal to s2n minus s2n minus, we have by hypothesis subdivision b 0 equal to limit n tends to infinity a2n equal to limit n tends to infinity s2n minus limit n tends to infinity s2n minus 1. This value is l, this value is m. So substituting this place, we get equal to l minus m. Thus l equal to m, and so both s2n n varies from 1 to infinity and s2n minus 1 n varies from 1 to infinity converges to l. Hence summation n varies from 1 to infinity minus 1 whole power n plus 1 an is convergent. Next topic is conditional convergence and absolute convergence. Definition. Let summation n varies from 1 to infinity an be a series of real numbers. Subdivision a, if summation n varies from 1 to infinity modulus of an converges, we say that summation n varies from 1 to infinity an converges absolutely. Subdivision b is if summation n varies from 1 to infinity an converges but summation n varies from 1 to infinity modulus of an diverges, we say that summation n varies from 1 to infinity an converges. So this is the definition. Next theorem, we have proof. Statement is if summation n varies from 1 to infinity an converges absolutely, then summation n varies from 1 to infinity an converges. Proof. Let Sn equal to a1 plus a2 plus etc. plus an. To prove that Sn n varies from 1 to infinity converges, to show that Sn n varies from 1 to infinity is Cauchy. So by hypothesis summation n varies from 1 to infinity modulus of an is less than infinity, and thus Tn n varies from 1 to infinity converges, where Tn equal to modulus of a1 plus modulus of a2 plus etc. plus modulus of an. Given epsilon is greater than 0, there exists n belongs to cap psi such that modulus of Tm minus Tn is less than epsilon. M, n is greater than or equal to caps n. But if m is greater than n, modulus of sm minus sn equal to modulus of an plus 1 plus etc plus am modulus. So less than or equal to modulus of an plus 1 separate modulus we have. So less than or equal to modulus of an plus 1 plus etc plus modulus of am is equal to modulus of tm minus tn. Thus modulus of sm minus sn less than epsilon m comma n is greater than or equal to caps n. This proves that Sn n where is amount to infinity is Cauchy. Hence the proof. Next, unit 4, test for absolute convergence. Test for absolute convergence. So definition is, let summation n varies from 1 to infinity an and summation n varies from 1 to infinity bn be two series of real numbers. Summation n varies from 1 to infinity an is dominated by summation n varies from 1 to infinity bn. There exists n belongs to I such that modulus of an is less than or equal to modulus of bn. N is greater than or equal to caps n. There is modulus of an is less than or equal to modulus of bn except for a finite number of values of small n. Summation n varies from 1 to infinity an is less than or equal to summation n varies from 1 to infinity bn. Next theorem, let n equal to 0 to infinity be a sequence of real numbers. Then subdivision A is, if limit supremum n varies from infinity n tends to infinity n into root of modulus of an equal to 0, the series summation n equal to 0 to infinity an x power n converges absolutely for all real x. Subdivision B is, if limit supremum n tends to infinity n into root of modulus of an equal to L is greater than 0, then summation n varies from 0 to infinity an x power n converges absolutely for modulus of x is less than 1 by L and diverges for modulus of x is greater than 1 by L. Subdivision C is, if limit supremum n tends to infinity n into root of modulus of an is equal to infinity, then summation n equal to 0 to infinity an x power n converges only for x is equal to 0 and diverges for all other x. Next we have to prove we have n into root of modulus of an x power n equal to modulus of x into n into root of modulus of an. Thus if limit supremum n tends to infinity n into root of modulus of an equal to 0, then for any x limit supremum n tends to infinity n into root of modulus of an into x power n equal to modulus of x into 0 is equal to 0. Summation n equal to 0 to infinity an x power n is absolutely convergent. This proves subdivision A. To prove subdivision B, we have limit supremum n tends to infinity n into root of modulus of an x power n equal to modulus of L into x. So summation n equal to 0 to infinity an x power n will converge absolutely if modulus of L into x is less than 1 and diverge if modulus of L into x is greater than 1. This proves subdivision B. So the proof of C is left to the reader. Thank you, students.